turn this on?
I
don't think it's on.
A lot of you don't know, but Dan was my advisor, so he taught me how to grow by MOCVD, which I'm grateful for. A lot of you guys here are learning the MOCVD technique, which I'm grateful for too. What it doesn't say in his bio is that he helped pioneer the MOCVD technique at Rockwell Science Center. MOCVD was patented and came out of Rockwell Science Center in the early 70s, I guess late 70s and early 80s. And then he took that to USC and really was the first academic effort in MOCVD. I think there's many firsts that was demonstrated. The first semiconductor laser by MOCVD, the first HBT electronic device, and also the first solar cell by MOCVD. So a lot of firsts, and then he's continued to pioneer several devices with that. Currently, he's the director of the Energy Frontiers Research Center at USC, which is called the Center for Energy Nanotechnology. He's got too many awards, so I won't mention the long list of awards. Just that he's been well recognized in the field, and it gives me great pleasure to humiliate him here in front of all my colleagues after graduating, whatever it was, 25 years ago. Okay, thanks, Dan.
Thank you. Thank you, Steve. You know, everybody should be lucky enough to have a progeny like Steve. What a great guy. And I appreciate your comments. I want to talk today about some portion of the work that is being done in the Center for Energy Nanoscience, which is an EFRC, much like the one that you have here. The original title of it was Emerging Materials for Solar Energy Conversion and Solid-State Lighting. Well, that didn't, you know, how could you say that repeatedly? So we changed it to the Center for Energy Nanoscience. And let's see, for some reason, this guy is not advancing. There you go. So the center, I'm not going to review all of the efforts that are going on in the center. Okay. Just say restart later. Tomorrow. Okay. What's going on here? Okay. So what it may be the, no, okay. I'm only going to review a portion of the work, and the reason for that is that our center is aiming at trying to develop scientific understanding to improve the performance and hopefully the cost of LEDs and solar cells. And we are working in two different materials technologies, semiconductor nanostructures and organic materials. I am fortunate to have an associate director, Mark Thompson, who's an expert in many aspects of organic materials, and so I never had to learn very much about them. And so I won't try to talk about them and embarrass myself, and I'll probably embarrass myself enough talking about semiconductor nanostructures. So we have a strong group of people working in both of these areas. We've got some pretty sophisticated characterization tools, and we've got a very powerful capability of doing atomic atomistic simulations based on our capability at USC in the High Performance Computing Center, which by some estimates is like the fifth fastest, or fifth most powerful academic computer on Figueroa Avenue in Los Angeles or something, you know. People always adjust their descriptions to make it sound impressive, but it's really a fine facility. So I'm going to focus today entirely on the semiconductor nanostructures and really focus more on the efforts that are going on in my own research group, although I work collaboratively with several other faculty members, and I'll try to recognize their contributions as we go along. Okay, so I'm going to talk about two kinds of devices today. One is a multi-junction solar cell based on nanotechnology, and the other are LEDs based on nanostructures. in the case of multi-junction solar cells, we chose to emphasize this approach because to date, only multi-junction solar cells have actually produced efficiencies greater than the Shockley-Queisser limit. There are many concepts out there for sort of third-generation solar cells. None of them have really proven to be successful in any venue, and so we decided to focus all of our effort on multi-junction solar cells and hopefully come up with a way that might make them lower cost in the long run. So recently, a group at Solar Junction has made like a 44% efficient triple junction solar cell. But it involves the growth of 3 materials that are all lattice matched on a gallium arsenide substrate in this case, including a quaternary material grown by MBE, of all things, you know. So we all know it's not practical, right? I'm sorry, I just can't stop, you know. I've been doing this for 30 years. I'm not going to stop now. Yeah. So anyway, you know, these solar cells are great. I mean, they're flying in space. Not this particular brand, but ones on a germanium substrate are flying in space. They provide most of the solar power for communication satellites and him? Is he powered by one too? Oh, okay. You know, it's a real technology, but it's a very expensive technology, and it fills that particular important application, but may not be transferable to the terrestrial environment. So the question that we ask ourselves is how can we translate this expensive approach to hopefully a lower cost platform? It'll be up to you to decide whether we have any hope of doing that. So far, it's we're struggling. But so if you've worked in solar energy at all, you've seen this kind of view graph many times before. And I only point out that this is sort of the Shockley-Queisser prediction for the maximum efficiency of a single junction solar cell. It's about 31%. Depending on how you do the calculation, it varies from 31 to 32, 33%. But nonetheless, it's right in this range. And as far as I know, there's only one device, a recent work out of Alta devices, a gallium arsenide solar cell, that's actually achieved very close to the Shockley-Queisser limit in efficiency. And most of these other dots here, which represent the best research devices for a particular technology at the time that, at the year that they're plotted here, fall well below that. The only ones that exceed the Shockley-Queisser limit are the multi-junction solar cells. Okay. So that's why we targeted this, and I don't know if I'll convince you that we're on the right track, but that's what we're trying to do. Whoops. Okay, so solar cell, particular multi-junction solar cell, is basically an integrated device already. It involves the use of multiple materials that absorb different colors of light that are grown in sequence, one on top of the other, the highest band gap on the top, lowest on the bottom, and they're interconnected electrically usually via a tunnel junction. So in order to make a successful solar cell of this sort, you have to make good, efficient solar cells out of 3 different types of, 3 or more types of materials, and then develop the interconnect technology to be able to electrically connect them so that you add up the voltages from all 3 cells. The other part of the trick here is that you need to match the currents from each of the cells. So the absorption properties, the absorption threshold, the thickness of the layers and whatnot all have to be carefully tuned in order to match those currents. So we did some modeling early in the program based on paper by Chuck Henry back in the dark ages where he calculated limiting efficiencies for single and multi-junction solar cells, basically extending the Shockley-Queisser paper to multi-junction cells. And what I'm showing here is a table that shows the ultimate efficiency that you can achieve for 1, 2, 3, 4, 5, and 6 junction solar cells. Now at some point, I think he calculated all the way up to 72 junctions. At some point, I have to question the credibility of that sort of plan. But nonetheless, the cells here, so what's shown here is the efficiency that you can achieve from this number of cells in the same spirit as the Shockley-Queisser limit, and the band gaps that you need to use in order to properly segment the solar spectrum. And this is for an air mass 1.5. So, you know, for a single cell, it's well known that this is in the range of 1.3 eV. For 2 cells, you need one that's about 1 eV and 1.7 eV. For 3 cells, it breaks down as 0.8, 1.3, and near 2 eV, etc. And so you get the scheme here. So if you translate that into materials, then this can be indium phosphide, gallium arsenide, even silicon is pretty close to the maximum. When you start going to 2-junction cells, then you have to match something that has a band gap of about an eV with something that's 1.7 eV. And the options that you have when you consider the fact that you need a strongly absorbing material, so you need high absorption coefficient, you need to be able to make PN junctions and heavily doped PN junctions, means that you have to focus on the 3-5 semiconductors pretty much, as best we know today. And these are the 3-5 materials that where you can achieve 1.7 eV band gap. So if you go to 3 junctions, then you can use germanium, indium gallium arsenide, and gallium indium phosphide, etc. You'll notice that in several of these possibilities, and incidentally, this is indicated without any concern about the lattice constants of the constituents. So we're not worried about lattice matching in this exercise. And what you see is that silicon is kind of an ideal material for a lot of purposes. But you have to be able to grow high quality 3-5s, which are not lattice matched, onto the silicon. And that's something that, you know, people have spent lots of energy trying to accomplish without a great deal of success when you talk about epitaxial thin films. And so we're looking for an approach that would allow us to integrate these materials with silicon monolithically. Okay, so that's sort of the background motivation for what we're going to talk about. And the approach that we're using is to replace the epitaxial thin films with nanostructures. In this particular case, nanowires or nanorods, depending on what you might want to call them. And the idea here is that because these materials can be grown, because the dimension of these materials can be architected so that they're very small in a lateral dimension, you have the possibility of growing these things on a lattice mismatch substrate without getting the dislocations that typically occur at lattice match interfaces propagating into the material. And that's sort of a fundamental idea behind why we're trying to do this. So the other idea is that if we could accomplish this and say use a silicon single crystal substrate here, we could leverage that technology, which is already well developed. Now the advantages of nanowires is that the dislocations within the nanowires are either eliminated or reduced by two effects. One is spatial filtering. If you're only covering 10% of the area here with nanowires, you will miss any dislocations that happen to be in the substrate, although in silicon that's not usually an issue. But in addition to that, the dislocations tend to bend over towards the sides of the nanowire as it grows and don't propagate all the way to the top of the nanorod. We can vary the composition here and adjust the band gap and absorption threshold. And what I'll show you in a minute is that this kind of a design actually gives you a measure of optical concentration. And I'll explain that in just a minute. In addition, because of light scattering amongst these rods, this kind of a structure actually has natural anti-reflection properties. One of the big problems in a multi-junction solar cell is getting low reflectivity over the wide energy band that you require for a multi-junction cell. And these kinds of structures automatically give you that kind of low reflectivity. So there are a number of reasons why it's interesting to look at this. And that's what we've chosen to do. Now, when you talk about a multi-junction cell, you have a couple of possibilities. You could stack the materials one on top of the other, and this is I try to indicate that with the color of the portions of the bar. So the lowest band gap is on the bottom, intermediate and top, like this. And under those circumstances, the light has to pass sequentially through the different cells, much the same as it would in an epitaxial layered structure. We could also think about using a core shell kind of a structure. It turns out that that's not very practical because, for one thing, the light will light of all colors will be incident on all of the materials. You don't get the spectral separation that you're hoping to achieve with a tandem cell, for one thing. And secondly, the thickness of these layers in order to absorb the light above their band gaps would have to be substantial. And all of a sudden these things are no longer wires, they become just chunks of material. And so we're focusing on trying to accomplish this thing. So the questions that arise is, how does current matching constrain the geometry, and are optimal band gaps the same as for bulk? And how can the material volume be reduced without sacrificing efficiency? Well, we're fortunate to have a young person in our department, Michelle Povinelli, who is interested in calculating the optical properties of these kinds of structures. And she's done very extensive simulations of the absorption and transport of light through these kinds of structures. And she operates from the premise that if you can take the absorption property of the material, you can calculate sort of what the ultimate efficiency is through a simple model like this. And that establishes an upper bound on the efficiency, much in the same as the Shockley-Quasar limit. But she's taking into account the full details of this three-dimensional structure and doing full-scale simulations on our HPCC system to calculate how the light propagates. So one of the first conclusions that we reached is that, in fact, even though the surface might be sparsely covered by these nanorods, because of the high index of these materials compared to the surrounding air, light tends to be concentrated in the nanorod. So, whoops, I'm sorry. And so, for example, if you have only 10% of the area covered, you get roughly a factor of 10 concentration of the light within the dielectric medium. And that has certain advantages because that means that the current per unit area generated in these structures will be 10 times higher, and you get some of the advantages of concentration, although modest concentration, by using this kind of structure. Now, I don't have the time today to cover all of the work that she's done, but she's done a very extensive modeling of individual materials as well as multi-junction combinations of materials, and is now actually calculating current transport in these structures so that she can calculate real absolute efficiency. And the conclusions are this. One is that because of this light concentration, the height of these nanorods need not be any greater than the thickness of a film that you would put there to absorb an equivalent amount of light. So, for example, gallium arsenide has an above band gap absorption coefficient of 10 to the 4th reciprocal centimeters, and in order to absorb 95% of the light, you need something that's about 3 microns thick. Similarly, nanorods need only be 3 microns tall, provided that you have optimized the lateral geometry and the spacing to achieve the same amount of absorption. So what that means is that we gain about a factor of 10 in terms of materials usage. And that's always an issue when you talk about large-scale usage of solar energy, because the materials we're dealing with here are not particularly abundant materials. Okay, so I'm just going to flash up a few results that she has modeled, or her group has modeled. Gallium arsenide directly on silicon. It turns out that we can achieve nearly the limit efficiency with gallium arsenide on silicon, even though they're not exactly current matched. And we do that by limiting the height of the nanowire so that some of the light gets absorbed in gallium arsenide and some of it that's above the band gap leaks through and gets absorbed in silicon so that we can current match the structure. She's looked at gallium arsenide along with AlGas and indium gallium phosphide, and the numbers that she's calculating are very respectable efficiencies on the order of 30 to 40%. In all of these cases, we're sort of looking at the nanowire solar cell as a way of enhancing the efficiency of the silicon cell in the short term. In the longer term, we'll be more aggressive. Okay, so I've talked about what the potential advantages of using nanowires are. The question is, how do you fabricate these things? And there are several different ways that people have employed over the years. The approach that we've used is selective area growth. And the idea here is that you start out with some substrate. In the longer run, this might be silicon, or it might be an amorphous substrate. You pattern it with a nanoscale opening in a dielectric film, and then grow from the vapor phase, gallium arsenide or whatever material you're trying to grow, and control the growth conditions so that the growth is primarily vertical, so that you limit the amount of lateral growth and you can form very highly asymmetric structures by doing that. And so it's necessary to control the growth kinetics of the various facets in order to achieve that. Let's see. Now, this is to be contrasted with vapor liquid solid growth, in which people have done extensive amount of work by using, say, a small ball of gold or some other intermediate metal that absorbs the vapor phase reagents and then redeposits the material underneath as the ball propagates upward. The difficulty with that is that that ball acts as a reservoir of reactants, and so it's very difficult to change composition. It's very difficult to change doping abruptly. And if you remember that we have to do both of those in order to make tunnel junctions and abrupt transitions between materials. So we focused on this particular approach. Now, right now, all of the work that I'm going to talk about today, we've used electron beam lithography to open up the holes. I'm probably not going to argue that that's the best way of doing it in the long run if you're trying to make cheap solar cells. And there are a myriad of other ways of making nanoscale openings for example, we've used spin-on layers of dielectric spheres where we utilize the blocking properties of the spheres to create periodic arrays of openings. We've also used imprint lithography and projectional lithography. You'll see that the kind of openings that we're talking about here are in the range of 150 nanometers and above. And that's getting well within the range of projection lithography at this time. And so it has, it looks like it could be a manufacturable technique. All right, so I have a whole story about what happens when you grow different materials on various substrates in this way, and I tried to summarize it with one view graph. At the risk of cutting out too much discussion, let me just say that in order to grow these as nanorods, using MOCVD as a growth method, so that the nanorods are vertical and well controlled laterally, you have to grow so that these structures are growing along the 1,1B orientation. Okay? So a lot of the work that we've done just to do experimental research is we've chosen substrates that are 1,1B, and we can grow arrays of nanorods to almost arbitrary, well, let me not exaggerate. We can grow them pretty tall and still maintain very narrow lateral dimensions. The surprising thing is that, and all of them grow as zinc blende crystals. The surprising thing is that indium phosphide, which is one of the materials that would show up among your choices for a lot of different reasons, doesn't grow along the 1,1B direction at all by this selective area growth technique. In fact, you have to grow it along the 1,1A direction, and when you do, it grows not as a zinc blende crystal, but as a wurtzite crystal. It really kind of surprised us and created some problems for us because some of the alloys that we thought we'd like to make, like indium arsenide phosphide or indium gallium phosphide, won't grow as nanowires because of this difference between the properties of indium phosphide compared to the other 3,5s. Of course, gallium nitride wants to grow along the 0001 direction, either the gallium or nitrogen face. You can grow nanorods, but we'll talk about that later. So we looked into why this might be happening, and this is kind of a busy view graph. You have to accept the idea, which we borrowed from the MBE literature, actually, that when you grow on this particular facet, the 1,1B facet, the surface reconstruction is such that the surface is stabilized when there's an extra layer of column 5 atoms on the surface in the form of trimers that are bonded to the surface. And this gives you a 2x2 construction, and this is very well established in the MBE literature. Of course, we don't have the ability to look at those kind of structures in the MOCVD system. So we're hoping and assuming that that's what happens in MOCVD as well. Now, so the question is, why would that impede the growth of indium phosphide on the 111B surface? And if you look at the bond dissociation energies of between arsenic and phosphorus and compare that to the indium phosphide and the gallium phosphide bond dissociation energies, you find that the phosphorus bond energy is greater than the bond energy between indium and phosphorus. Whereas in all other cases, the bond energy between the 3 and 5 element is greater than the bond energy of the 5 to 5 bonding. So our simplistic explanation of this is that when the surface gets reconstructed in the growth of indium phosphide, whatever we do to break these phosphorus-phosphorus bonds in order to let indium adhere to the surface and grow another monolayer will be sufficiently aggressive that it will also attack the indium phosphide bond. And so we get into a situation where we can't find the right conditions in order to grow indium phosphide. Now, it's, this is fragmentary evidence, but it is the only case for which these bond dissociation energies are ordered the way they are, and it's the only material that won't grow as a nanowire on the 111B orientation. And so we think that's strong evidence that that's what's happening in this particular material system. So the consequences of that is that mixed alloys of indium phosphide won't grow vertically on that orientation, and indium phosphide mixed alloys then probably will have to be restricted to growing as a radial layer on as a core shell kind of a structure. I'm not going to touch on this again as we go forward, but this is a case where the surface reconstruction is actually controlling the kind of crystal geometries that you can grow in this field. Okay, so let me show you what happens just with a brief picture when you grow gallium arsenide on a 111A surface and a 111B surface, where we've patterned the surface with openings. On the B surface, we grow a regular array of very nice nanowires, whereas on the A surface, what happens is we grow nanowires, but they grow off at angles, and they actually pick up the 11B direction in the crystal. Okay. Now, you see lots of stuff in the literature that looks like that, but I like the look of that, so we focused on that. One of the consequences of this way of growth is that if you look in TEM at cross-sectional TEM at these nanowires, be they gallium arsenide, indium arsenide, gallium phosphide, any of these materials, also grown not only by the selective area growth but also by VLS techniques, what you find is there is a very dense array of stacking defects. And in some cases, there's actually mixed phases here where some of these layers are wurtzite and some of them are zinc blende. In the case of most of the materials that we've talked about, they're all wurtzite materials, except that the crystalline symmetry rotates by 180 degrees at a twin plane. So I'm sorry. Oh, I got ahead of myself. Remember those thoughts, I'll come back. Okay. We've also grown gallium arsenide nanowires where we use gallium itself as a catalyst, or I call it a solvent, to grow nanowires out of a ball of gallium. So we deposit gallium in the openings on the surface and then grow by MOCVD, and we can form nanorods at actually pretty high growth rates and quite uniformly. There doesn't appear to be a great advantage to this over the direct selective area growth in terms of the properties of the material, so we haven't focused a whole lot on that.
Was there SiO2 that gallium is hold in there or not?
I'm sorry?
Is there an SiO2 mask on that when you started?
Yeah, there is. There's a SiO, well, it's silicon nitride in our case, but yeah, there's a mask with an opening. And what you're looking at here is the top of a hemispherical deposit of gallium. So we just turn on the gallium for a while at elevated temperatures and then pull it out of the reactor and looked at it, and there's gallium balls pretty uniformly distributed in those holes. And then when we grow the nanorods under the right conditions, they will go directly out of that.
So that's trimetal gallium turned on?
Yeah.
And with no other nitrogen
Well, yeah, carrier gas, but
no.
no column 5 or anything else like that.
And what's the spacing on that?
So in this particular case, it looks like they're about 500 nanometers and maybe a little bit more than 100 nanometers in diameter. But, you know, we've done this over a wide range of patterns.
And what size do you start to see deposition in the mass?
That depends on how, that depends on the conditions, how much reactant you put in there, okay? So basically, as long as you grow with a low enough flux that you allow the material to move around, and we grow under conditions which favor the migration of gallium on the surface here. So we don't see deposition ever, I think. I'm not growing them, so that's what my students tell me anyway. You know, you're a, all right, anyway. I don't want to seem too disconnected, huh?
Too out of touch.
Yeah. Yeah, that's one of the things that I tell my students all the time. I want to see the bad results. I don't want to see, because there's a tendency, you know, I have them write weekly reports and they send me all the beautiful pictures. And I think, yes, and I'm selling things, and then I find out that, well, maybe that was a selected piece of data. This is not. I've seen enough of it to know that, I think. Anyway, so we've applied this to the growth on silicon, and growing on silicon is tricky because there's a native oxide naturally on silicon, and because of the polar-nonpolar interface between silicon and gallium arsenide, getting the right ordering of the crystal on the surface is a challenge. But we've developed techniques based on a lot of literature that from the 80s and 90s where people did a lot of this work, so that we can control the fact that the surface is treated with arsenic. It's either got two-layer steps. Well, these are 111 surfaces. That doesn't apply, but they're treated with arsenic, so it's an arsenic-rich surface. And we grow ordered nanowires on the silicon surface. This shows a magnified or a demagnified image of one of those kinds of things.
Dan, the silicon is 111?
Yeah, yeah, in this particular case. So part of what we do is, in addition to our own work, is we're collaborating with the JCAP Center at Caltech and Berkeley. And this is the Energy Hub, where they're trying to do artificial photosynthesis, and basically they're trying to break water. And they need a junction device that has an output voltage of greater than about 2 eV in order to break water. And so they're looking at integrating gallium arsenide with silicon to get the right voltage that they need. So they've looked at some of the materials that we've grown at USC. In fact, one of their postdocs, Shuhu, works in my lab. And we haven't yet made a tandem cell out of the two, but what they have done is looked at the properties of these nanowires in a liquid solution, in a ferrocene kind of solution, and measured the photovoltaic properties. Now, in this particular case, since these rods are all surrounded by the liquid, it's essentially a radial junction, Schottky barrier kind of junction between the liquid and the nanowire. And we've achieved conversion efficiencies of about 8% using those. That's still well away from our goal, but it's not bad. It's one of the best results for gallium arsenide kind of solar cells. And the most important thing is that with this kind of radial core shell design, we're getting short circuit current densities which are very close to what you'd expect in an air mass 1.5 solar cell. So the other issue...
At what radiation intensity?
Pardon me?
At what intensity?
Air mass 1.5.
One sun, no concentration?
One sun. No concentration externally, but of course there's concentration in the wires. So that's an encouraging result, but it still is well short of what our goals are. Now, we've made nanowires on silicon and on gallium arsenide that are very, very pretty. These happen to be nanowires without any larger band gap cladding, and so we have a junction built in axially into the structure. We infill this thing with a low dielectric constant medium, and then make contact only to the tops of these things with a transparent contacting medium like ITO. Okay? And we've made solar cells out of them that are beginning to look like real solar cells. They have the right kind of shapes, but the efficiencies are still very low. And primarily, in this particular case, where we're trying to collect the current along the wire, the problem is the short circuit current is very low. So we need to first passivate these surfaces with a larger band gap material, and then develop the solar cell technology for that kind of a structure. And we hope that they'll improve significantly.
Does that current density already count for the area being reduced by 10?
No. No.
So does that mean the actual current is 10 times higher?
That means that the current is 10 times higher in the wire.
In the wire.
Yeah, right. Okay, so what kind of problems are we facing with these things? Well, for one thing, everybody knows that the surface of gallium arsenide is pathological. It's pinned at the Fermi level is pinned at the surface. The bands are bent in such a way that they attract minority carriers to the surface, and there's a plethora of states in the surface to recombine the carriers when they get to the surface. And so this is just a simulation to show that it also reduces the carrier concentration within the wire. So if you make a wire that's really small, like 100 nanometers, this one, you've got to dope it up to 10 to the 18th to get even 10 to the 17th average free carrier concentration in the wire, based on this model simulation. So that's a problem. The other problem, of course, is that the surface recombination velocity on these materials is very high. And we've measured very short lifetimes and diffusion lengths in these structures that are consistent with that. And so we've really got to passivate the surface with either AlGas or some other large band gap material. And when we do and look at the PL, we get a 30 to 100 times increase in the PL efficiency of the material, so indicating that we're reducing the amount of surface recombination. Whether it's enough to make a good solar cell or not remains to be seen. Well, okay, this happens to show an array of wires where we've coated them with AlGas, and you can see that the surface is relatively smooth, and in TEMs, the AlGas looks like it's uniformly coating the sidewalls of the surface. So we have not yet made solar cells out of these, and we're hoping to do so in the near future.
What is the thickness of the AlGas that you need to...
Good question. Good question. I don't know. We're shooting for several tens of nanometers. There's been some work done by other groups, Jagdish's group in Australia, where they're using relatively thin layers, thinner than I would have thought would be effective. And we have to do those experiments and see. Okay. So the other problem I alluded to earlier is the stacking defects. And in the selectively grown structures, these stacking defects are twins. That is to say, one layer is rotated by 180 degrees compared to the previous layer. And, well, let me go to the next slide. I think I show that. The normal stacking sequence for a zinc blend is ABC, ABC. And what happens is that at this interface, this bonding arrangement is such that the structure is rotated by 180 degrees. So it's still gallium arsenide. It still behaves in a lot of ways just like bulk gallium arsenide, except that for this stacked layer right here, the bonding is actually similar to a quartzite crystal. And so we might expect that there would be a discontinuity in the energy band at that point. My colleague, okay. So my colleague, Ichiro Nakano, using our high-performance computing system, has done a full quantum mechanical calculation of the energy band structures, given that you have this kind of rotation, and calculating the scattering rate that would obtain because of this discontinuity. And what he's discovered is that for the kind of separations between these twins that we observe, which are on the order of a nanometer, the mobility of majority carriers is limited by these twins. That is to say, if you look at this mobility, it's on the order of 1,000, increasing to maybe 2,000 at higher temperature. And that's comparable to what you'd see in material that's doped mid-10 to the 17th or thereabout in gallium arsenide. And so it's just as effective as impurities in reducing the mobility of the material. And so it's something that we chose to do some work on. Now, Ichiro also tried to see if this was an inherent part of the growth of these nanowires. He had done some work on zinc oxide in which he showed that nanowires actually form intrinsic core shell structures. Because of the relaxation of bonds on the surface, there is a relaxation of the lattice, a few lattice constants into the material, so that this is tetragonally distorted relative to the core of the structure, even in a pure material. Well, if you assume that that kind of structure exists in gallium arsenide, then look at the top surface, what you find is that there's certain energetically favorable positions for gallium to sit when you're trying to grow the structure. And it turns out that that favorable position would lead to quartzite type bonding arrangement. And so this is one possible reason why these rotations in the crystalline structure occur in these nanowires. But there's also been some work done in Japan at Fukui's lab where he's looked at the initial nucleation of gallium arsenide in small openings, and he's seen that the initial nucleation takes one of two forms. They're tetrahedron, and they're either aligned along the 1, 1, minus 2 direction or the minus 1, 1, 2 direction, which are 180-degree rotations of that tetrahedron with respect to one another. Upon closer study, he found that this is the preferred orientation for the growth of the quartzite crystal. This orientation quickly forms a twin boundary in the layer, so that the crystalline structure rotates by 180 degrees. So his model then for the formation of these nanowires is that you get these nuclei forming on the top of the structure that form either with this orientation or with this orientation, and that they, due to surface energy minimization, they end up rotating periodically through the growth of the structure. In the end, you end up with something that looks hexagonal, even though the 111 surface only has threefold symmetry. So we were acting on both of those inputs and decided to try to change.
A quick question.
In terms of luminescence, I don't know. I don't believe so. I don't know, though. We haven't done cathodoluminescence on them, and so we don't know. I don't know. Okay.
What is the dislocation density in the wires?
We've never measured a dislocation in the wires.
Do you think it's zero or you better?
Could, you know, it's statistics of small numbers, you know. TEM is tough. We look at some wires. We don't see any dislocations. And if I said there were no dislocations ever, you would holler at me. So we don't know. But we've never seen any. On the other hand, we got all these twins, which is plenty bad enough, you know. So what we did is we changed the geometry a bit. We said, look, if this thing wants to, these structures want to grow with this orientation along the 1, 1, -2 direction, why don't we form a thin stripe that's only 100 nanometers and see what happens. And sure enough, we grew sheets of material that, if you look at the details of the planes on them, look like they're a section cut out of a tetrahedron aligned along that direction. And I've got a whole story about this, and I want to rush through it because it's running late. But the bottom line is that there are no twins in that nanosheet at all. They grow perfectly with perfect 110 surfaces, no twins. And incidentally, when you grow them on silicon or when you grow them on gallium phosphide, all of the misfit dislocations form right here, and there are none that propagate into the structure. So it has some potential implications for integration on silicon or other lattice mismatch materials as well. Now, incidentally, this is a nanowire by comparison, looking at these two cross-sections. Okay, I'm going to skip ahead because I'm running late. And I want to get to the gallium nitride stuff. This is a kind of an exciting area. We're trying to grow these same kind of structures on other orientations of crystals so that we can make arrays of these nanosheets, which would be like a grating solar cell, and see what we can achieve with that without any dislocations and no stacking faults in the layers. But we're just at the threshold of doing that. All right, so I'm going to skip this story, and you forgive me if you will, just because I know I won't get done if I don't. Come on, Dan. See, you're following everything I'm doing here? Well, one of the things that, let me just say, I can't pass this up. One of the things that happens is that when the dimension of this nanosheet begins to approach like 100 nanometers or smaller, about comparable to the thickness of the nanosheet, then the top of that structure looks like an opening in the substrate, and we form twin. Okay, but you only form one twin. So you notice that this thing has these planes that define the angles of the facets here. And once this twin is formed, the thing is rotated by 180 degrees. Now all of a sudden the shallow angle is over here and the steeper angle is over there. So we looked at TEM of that, and sure enough, if you look at the Fourier transform of the diffraction over here, you get the expected pattern. The pattern over here is shifted slightly, and if you look at the region in between, you pick up the combination of the two, indicating that there's really just one twin boundary formed at that interface. And so, well, anyway, so that sort of lends credence to this model of the nanowire growth and says that these are inherent properties of nanowires grown in this particular way. Okay, so I'm not going to summarize that. I want to, well.
Go ahead, people can leave.
Huh? Hi. I want to talk about gallium nitride nanowires for LEDs. And I'm sorry that I'm running along, but I know you're all having fun. And what the hell? There's only beer to drink tonight, right? Okay, so in this audience, I'm sure you're all familiar with how current LEDs for lighting are fabricated. They have a gallium nitride emitter that pumps a phosphor, and the combination of the spectrum from the phosphor and the emitter gives you quasi-white light. Presently, those are for the vast majority of the products, they're grown on the C plane, which because of the particular ionicity of the bonds in the structure, leads to a piezoelectric effect that creates an electric field in the vicinity of the quantum well that displaces the electron and hole wave functions unless you make these wells really thin. So empirically, even before all of these effects were understood, I believe, people made these quantum wells here only 2 to 3 microns, 2 to 3 nanometers thick. And there are some downsides to that. And so we wanted to explore, like is a big effort here at UCSB, the growth on nonpolar substrates. So let me skip ahead. This is all PR. So what we're doing is to use C-plane sapphire, grow bulk gallium nitride on it, form a pattern on the structure, and then grow nanorods perpendicular to the substrate. And these nanorods naturally form with 1 bar 0, 0 surfaces, namely M-plane surfaces around the perimeter. So the idea is that since these structures, these planes are nonpolar, that we can grow quantum wells in a core shell kind of arrangement so that there's no electric field or there's no strong electric field perpendicular to the quantum wells, and hopefully achieve the same sort of thing that Shuji and the people here are trying to achieve with gallium nitride bulk substrates. And so it would enable you to make thicker quantum wells and to do all of the things that might promote devices with less droop, etc. We've also looked at structures where instead of nanorods, we've structured the pattern so that we grow nanosheets of gallium nitride with M-plane surfaces, and we can grow quantum wells on these surfaces as well. So, growth of these kind of structures requires the control of the kinetics of growth. Typically, if you grow under conditions that you would normally use for gallium nitride bulk material, you tend to form pyramids like this that are made up of the M-planes and what we call the tilted M-planes, which are 1, minus 1, 0, 1 planes here, that are the slowest growth planes. And if we were to continue to proceed here, what would happen is this structure would form a pyramid on the surface. And that may be useful, but our objective here was to grow on these nonpolar planes. And so we needed to control the kinetics of growth here so that we can form tall nanorods with M-plane surfaces. So we've devised 2 or 3 different growth regimes in order to do that. This just shows some examples to convince you that we can do it, and that it's we can do it on different center-to-center spacings and with different openings in the rod. And in all these cases, you find that the surfaces are M-plane surfaces. Now, recently we've developed a continuous way of growing that is to say where we continuously feed the reactants into the reactor, and we get fairly high growth rates. Previously, we were hindered by the kinetics of growth to fairly low growth rates, but now we can grow at rates that are comparable to epitaxial growth. Similarly with the nanosheets. Well, there's just an example of the kind of nanosheets that we can form. So, what I want to show here, and there's part of this audience that's seen this stuff already, but I apologize. We've grown we've grown quantum wells on the facets of such a nanorod. And it turns out that in this particular experiment, there was still a residual C-plane up here when we grew the quantum wells. And so I'm going to show you the cross-sectional quantum wells in this region where we're on the, what we call the tilted M-plane, the semipolar plane here, on the polar plane, and then up here at the tip. And all of this material is hexagonal material. We see no dislocations propagating from the substrate. We have only once encountered a dislocation in doing TEM, and that one bent over to the side. Someone would argue that that's not a big deal, but I kind of like it. So, what we decided from this study is that if you grow on the C-plane, the growth rate is about a factor of 2 higher than if you grow here on the M-plane on the side. But the growth over here is exceedingly slow, about a factor of 3 or 4 less than the growth rate over here. So when we have all of these facets available, we'll grow the desired quantum wells on the side wall. We'll grow very thin quantum wells over here, and actually pretty thick quantum wells over here. So we've devised ways of growing under conditions where we pinch off the C-plane, so there's no C-plane when we grow the quantum wells. And under those circumstances, we haven't been able to measure any quantum wells up at the tip of the structure, and we have only the ones that grow here and small ones that grow here. This just shows a cross-sectional TEM, and you can see that the quantum wells are continuous and fairly uniform around the structure. This is another image taken from a structure we grew later in our development, and it shows the quantum wells and how they change, or how the growth changes in the vicinity of the intersection of these planes. We believe that because the growth rate is so slow here, reagents land on this surface, diffuse down to this region, and so we get thicker growth rate in the collar around the two regions, but still have very thin quantum wells up here. So we've looked at those nanowires and looked at catholuminescence. This is one that if you did PL or CL on it, would emit at about 450 nanometers. And what we see is that the majority of the sidewall emits in the range of 430 to 450. And only the region right around the collar here, where the growth rate was greater, the layers are thicker, and perhaps the indium concentration is higher, do we see longer wavelength growth that accounts for this extra peak here in the emission spectrum. So we're pretty happy with that. On the other hand, we have seen some in which we didn't efficiently pinch off the C-plane, where we get fairly non-uniform growth, and we actually get a chunk of long wavelength emitting material up here at the tip of the nanorod. So we're working to understand the kinetics of growth to make sure that we understand how to control that and to eliminate it. Okay. So how do you turn these into LEDs? Well, one way to do that is to take the nanorods with the quantum wells and then grow a P layer that coalesces the layers so that we have a P layer that contacts the outer perimeter of all of these nanorods. We do that while embedding the mask region here by changing the growth conditions. And we've made LEDs out of that structure. We're still fabricating these things with E-beam lithography, so the structures are small, and this just shows the emission from one of them. That's not a true color emission, it's a false color image of the emission. These structures show fairly stable wavelength of emission. There is a slight variation that we think may be related to the non-uniformities that we see in the nanorods. And the light output is a function of injected current. I'm sorry. Forgive me. Give me too many buttons, I go crazy. The light output is a function of current density, and this is current density into the entire chip. Now, one of the advantages of these nanorods is because the surface area is increased over what you would have for a planar area. The actual injection current density into the sidewalls of the nanorod is reduced, which could be advantageous for reducing droop. Nonetheless, we're not well set up. This is done with a probe, so it's taken on a point-by-point basis, and the efficiency as a function of current shows a slight bend over and a slight amount of droop. But this is a very early device, and we hope that we'll get better data in the near future. Okay, so summarizing, the gallium nitride nanorods are successfully grown. I'm sorry, why did I do that? The growth of quantum wells on end planes is confirmed, and the light emission is predominantly from the end plane sidewalls. We're looking forward to getting more rigorous measurements on these structures and finding out whether in this geometry we get a distinct advantage. And that will involve measuring absolute efficiency of the devices, which we haven't done yet. We're still measuring relative efficiency. So with that, I would like to acknowledge the students involved in the work. These guys are people in my group and the faculty who've been involved, Chungwoo Zhao, Michelle Povinelli, Achiro, and Steve Cronin, and then finally Shu Hu from Caltech, who works with us on the tandem nanowire structures. With that, I'm sorry for running long, but that's the end. You're done with listening to me. I'll be happy to answer any questions for those of you who have the courage to stay around. Yes, sir.
So you made your nanopillars about 100 or 200 nanometers in diameter to begin with. Is there any reason why you couldn't start out at, say, half a micron or a micron?
Okay, so we anticipated the issue of being able to pinch off the top so that we didn't get a C-plane up there. That occurs by growing under conditions where the growth rate of these sidewalls or these inclined planes is low. And so when you do it, the wires get fatter and the portion that's an M plane gets smaller. So there's a company trying to commercialize this Glow up in the Bay Area, and they seem to make bigger nanowires than we do, and they also they're wider separated apart than ours are. So we may find that that's advantageous, but right now we're sticking to the thinner ones.
You expected increased absorption due to nanopillars also. Do you also expect increased extraction for LEDs?
Increase extraction of light from these structures? Well, we modeled that. Michelle Povinelli has modeled that. And I think what I would say is that, current LEDs are pretty good. They're getting maybe 80% of the light out of the chip. I don't know that we're going to make a major improvement in that. But what we might be able to do by using photonic crystal kinds of effects is shape the emission direction. So we're looking at those kinds of issues. I don't think we're going to make a major improvement in the extraction efficiency.
Last question?
How do you think the efficiency or performance in like slabs, normal epitaxium, and just etched wires?
Okay. So in my experience, an etched, okay, so I started out naively thinking that a grown surface is going to be pristine and that's going to be advantageous. And I agree with your skepticism at this point. I don't think that if you etch it, you're going to be able to recover a clean surface without extensively reducing the diameter by etching. And so we just have tried to adopt the philosophy that we want to use the minimum amount of material, and that's why we're not trying that, or not doing that.
So you use like the etch for the InGaN phosphide or something, and then grow, like, could you grow out just on top of nanowire instead of in holes?
Sure.
Yeah.
Yeah, sure. Yeah, we've done that.
Okay, last question to you.
So there has been report on that by changing the size of those nanorods, nanowire, they can achieve multi-wave function operation on a single chip, such as for nanowire devices, they can see red, green, and blue, and they can achieve white lighting.
Right.
So do you have any experience in your lab on this?
Yeah, I skipped over that data. We've seen that as well. Just by changing the diameter of the nanowire with the same pattern, growing in the same conditions, we see a wide variation of the light output. My concern is that when these wires get kind of chunky and you grow them under the same growth conditions, they also get kind of short. And I think most of the emission is occurring from the tip of those nanowires where there's still a residual C plane. And it might be useful, but you know, whenever we've grown material where we push the indium concentration up, the efficiency has dropped dramatically. And I expect that will happen on those, but we're going to look at that more carefully.
Okay. So,
Oh,